Space is vast and full of wonders, a seemingly infinite expanse that has fascinated humanity for centuries. It's also home to some of the most extreme and mysterious objects ever discovered, black holes, which continue to intrigue scientists and astronomers alike. These enigmatic objects are regions of spacetime where gravity is so strong that nothing, not even light, can escape their grasp. Imagine a place where the very fabric of spacetime itself is bent to its absolute limits, creating a cosmic abyss from which there is no return. Black holes are a consequence of the fundamental laws of physics, specifically Einstein's groundbreaking theory of general relativity. This theory tells us that massive objects warp the fabric of spacetime around them. Much like a heavy object placed on a flexible surface, think of a bowling ball placed on a trampoline, causing it to sag under the weight. The ball causes the trampoline to sag, and the heavier the ball, the more the trampoline sags, illustrating how mass distorts spacetime. Similarly, massive objects like stars and black holes warp spacetime around them, creating deep gravitational wells. Black holes push this warping to the extreme, creating regions where the gravitational pull is inescapable. They create a gravitational well so deep that anything that falls in can never climb back out, not even light. This is because the escape velocity, the speed required to escape the gravitational pull, exceeds the speed of light, the universe's ultimate speed limit. The study of black holes is a journey into the most extreme environments in the cosmos, pushing the boundaries of our understanding. It's a journey to understand the fundamental nature of gravity, space, and time itself, and how these elements interact in the most intense conditions. So, let's embark on this journey together and explore the mysteries of these cosmic abysses, uncovering the secrets of the universe. Not all stars end their lives as black holes. The fate of a star is determined by its mass and the processes it undergoes during its lifetime. Our sun, for instance, will eventually become a white dwarf, a small, dense remnant of its former self. However, stars much more massive than our sun have a different fate awaiting them, one that is far more dramatic and violent. Their life story is a tale of immense gravity, nuclear fusion, and ultimately a spectacular collapse that defies imagination. Stars are cosmic furnaces powered by nuclear fusion in their cores, where hydrogen atoms fuse to form helium, releasing energy. This fusion process releases tremendous energy, creating outward pressure that counteracts the inward pull of gravity, maintaining a delicate balance. This delicate balance between outward pressure and inward gravity is what keeps a star stable, allowing it to shine for millions or even billions of years. However, this balance cannot last forever. As the star ages, it undergoes changes that disrupt this equilibrium. As a massive star runs out of nuclear fuel, the outward pressure from fusion weakens, and the star begins to lose its battle against gravity. Gravity, always relentless, gains the upper hand, pulling the star's material inward with increasing force. The star's core begins to collapse in on itself, and this collapse accelerates rapidly, leading to a dramatic transformation. The core implodes, becoming incredibly dense and hot, reaching temperatures and densities that are almost unimaginable. This implosion sends shockwaves outwards, tearing the star apart in a brilliant supernova explosion, one of the most powerful events in the universe. The supernova expels the star's outer layers into space, seeding the universe with heavy elements that are essential for the formation of new stars and planets. Meanwhile, the core continues to collapse, crushing itself under its own immense gravity, becoming denser and denser. If the core is massive enough, this collapse continues until it forms a singularity, an infinitely dense point at the heart of a black hole, where the laws of physics as we know them cease to apply. Imagine approaching a black hole. The sheer magnitude of this cosmic phenomenon is both awe-inspiring and terrifying. As you get closer, you would feel its immense gravitational pull, a force so strong that it warps the very fabric of space and time around it. You would be stretched and squeezed by tidal forces, a phenomenon aptly named spaghettification. This is due to the extreme difference in gravitational pull between your head and feet. But before you meet that rather unpleasant end, you would cross a boundary of no return, the event horizon. This is the point where escape becomes impossible. The event horizon is the defining feature of a black hole, marking the limits of our observable universe. It's not a physical surface, but rather a boundary in space-time beyond which gravity's pull is so strong that nothing, not even light, can escape. This makes it invisible to the naked eye. Think of it as the ultimate point of no return, a cosmic one-way street. Once you cross the event horizon, you're forever trapped within the black hole's gravitational grasp, with no hope of escape. Inside the event horizon lies a region of space-time we can only speculate about. It's a realm where our current understanding of physics begins to falter. At the very center of a black hole, according to our current understanding of physics, lies a singularity. This is a point where density becomes infinite. A singularity is a point of infinite density where the laws of physics as we know them break down. Here, the known rules of space and time cease to apply. It's a place where space and time cease to have their usual meaning, creating a paradox that challenges our understanding of the universe. The event horizon marks the boundary beyond which our current laws of physics cannot fully describe what happens. It's a frontier of scientific exploration. It represents a fundamental limit to our knowledge of the universe, a boundary that beckons us to explore further. However, it's precisely this mystery that makes black holes such fascinating objects of study. They challenge us to push the boundaries of our understanding and explore the unknown. Black holes come in different sizes. Some, known as stellar mass black holes, are formed from the collapse of massive stars. These black holes are typically a few times more massive than our Sun, but squeezed into a region only a few miles across. On the other end of the spectrum are supermassive black holes, true behemoths lurking at the centers of galaxies, including our own Milky Way. These black holes can have masses that are millions or even billions of times greater than our Sun. They are thought to have played a crucial role in the formation and evolution of galaxies. Despite their differences in size, all black holes share the same fundamental characteristics. They are defined by their event horizons, points of no return beyond which even light cannot escape. And they all harbor singularities at their cores, points of infinite density, where our current understanding of physics breaks down. The study of both stellar mass and supermassive black holes provides crucial insights into the nature of gravity, the life cycle of stars, and the evolution of galaxies. They are windows into the most extreme environments in the universe, challenging our understanding of physics and pushing the boundaries of human knowledge.